Today is lecture 20. So in the last class we were talking about boundary condition, isn't it? So you could see how it's not easy basically to write down the boundary condition. But once you work out 2-3 problems, then you will master it. It's not difficult also. Let me also talk about another kind of boundary condition that is called pressure boundary condition. So this is very common boundary condition. But you will see when you start writing it, it's not so easy. So here is your body, and let us say it is subjected to some pressure. So you know what is the property of pressure? It is always perpendicular to the surface or along the surface normal, and it is compressive, isn't it? So let us say this is at pressure P. So what boundary condition should I write here? Or how do I write the boundary condition? Does anyone have some idea?
So can you repeat once? Last
So
sentence.
how do
What
I
did you?
write the boundary condition when pressure is acting?
Normal component of traction will be pressure.
Okay. And what about the shear component?
I think 0.
That's true. So as the body deforms, the pressure also changes its direction, and it always remains along the deformed normal, isn't it? So pressure always remains opposite to the outward deformed normal. So you can see it's not constant, isn't it? It changes as the body changes its configuration. So therefore it is also called a live load. It's a live load because it is changing as the body is changing its configuration. And if you have a load which is acting such that it does not depend on configuration of the body, then we say it is a dead load. So these are terminology in fluid mechanics. Okay, so I'll just say there is something called dead load also. Okay, so how do I, so as Pulkit said that the traction should be equal to, so basically pressure is acting only along the normal and there is no shear component. So that means the internal traction on those surface at the surface traction internal, from inside the body should be, that is the boundary condition. And internal traction, we know we can relate it to Cauchy traction sigma times the normal n. So that's the complete boundary condition, and this is in Eulerian form. Now, how do I write this in Lagrangian form? So, we know how to relate the two traction measures. So we know that sigma small and d small s, that's equal to P, the Lagrangian or the first Euler-Kirchhoff stress tensor, into big N into D capital S, and this is already prescribed to be equal to minus P small n, and then you have to multiply by D small s, right? So when you look at these two, you can say that P into capital N into D capital S is minus P into small n into D small s. And now you can use the surface transformation formula to say that ND small s is equal to det F into F inverse transpose into capital N into D capital S. Okay, and when you compare these two, you will just see that P into big N is minus P into det F into big F inverse transpose into big N. So this is your Lagrangian boundary condition. So you see, it's not so easy. In Eulerian it was easy, but not in Lagrangian. Okay, any question? Okay, so that's about boundary condition. You can expect one question on boundary condition in the examination. So if you have any doubt, you can always ask me later on. Okay, so this was about boundary condition. So you can now see that whenever you have to solve a deformation problem, you need to solve the linear momentum balance equation subject to the boundary condition, which can have both Dirichlet and Newman type boundary condition or also mixed boundary condition. Okay. So, one of the methods to solve any deformation problem is using finite element methods. Okay, and in finite element methods, the first step is to write down the weak form of balance equation, which is also called as the principle of virtual work. Okay, so the FEM is, is based on the principle of virtual work. So let us work out what is principle of virtual work. And they will also say it's a weak form of balance equation. Okay, so you remember the equation that we have derived. So that's divergence dot P and plus rho naught into body force is equal to rho naught times acceleration, right? So suppose that we are dealing with statics, so we can forget about this, assuming a statics. So then this is equal to 0. And this is also called a strong form of balance equation. Can you recall that this is second order in small f? So here in this term, P is first order in small f because P depends on big F which is first order in small f, and then you have divergence, therefore you get second order in small f, right? So it's a second order partial differential equation in a small f. But you will see that when you write down the weak form, it will be first order in small f. Therefore, we say it's a weak form. Strong because the order is second, and in weak because order has reduced to 1. So we say it's a weak form. Anyway, so to work it out, so what we say is that let us multiply the strong form of the equation with some test function. And they also say it to be virtual displacement. And I'll make it clear what exactly does it mean, virtual displacement or virtual velocity. Okay, and it's also called test function. So let us work it out. So you multiply with a test function and you further integrate this in the domain of the body, which is dv naught. Okay, so the first term for which we have to work out is going to be divergence dot p dot with eta into dv naught, isn't it? So let us try to work it out. So if we write this in indecision notation, so let's do that. Divergence dot p dot with eta. So this divergence dot p, you can recall it is del p over del xj dot product ej, isn't it? And then when you expand p, this is del p kl over del xj ek tensor product el and then dot with ej. So these two are going to get dotted, and what you get is delta lj, so j becomes l. So you have del p kl over del xl into ek. So that's the thing inside the bracket, and then you have to dot with eta. So this has to be dotted with eta. Let us say eta I ei. And so ek dot ei becomes delta ik. So I becomes k basically, right? So this whole thing is therefore del p kl over del xl into eta k. All right. Now, so I'm just going to write it here. Del p kl over del big XL eta k dv naught. But the same thing can also be written as del over del XL pkl eta k minus pkl del eta k over del xl, isn't it? Just using product rule. And then let us see what are each of the two terms individually. So the first term here, what do you think? What is this? pkl eta k. It is same as plk transpose into eta k, right? P transpose lk eta k. So you will see that this is actually divergence dot P transpose eta. You can work out the index notation and you will get this. Okay, so this is eta. And the second term is quite evident. It is P double contraction gradient of eta. Isn't it? So we can now substitute it back, and this becomes integration over V naught divergence dot P transpose eta minus P double contraction grad eta. Okay, so again the first term you can now use Gauss divergence theorem, and it becomes integration over surface. Instead of volume, it becomes integration over surface. Let us say S naught of P transpose eta dot with the outward normal, isn't it? Which let's say is big N ds naught. Okay, and the second term is as it is. Right? Now again the first term, why don't you bring this P on the other side? Then you know that P transpose becomes P. All right. So now you see this is the first term is the integration over the surface. What is P big N? P big N, if on surface you are prescribing traction, then it is that traction, no? P big N is referential traction, force per unit undeformed area, which we denoted by big T naught. So this is something which would be prescribed by the external agent on the Newman surface. So we can write it as integration over S naught N. So S naught N is part of surface where traction is prescribed. Okay, and then P into big N, we'll write it as some T naught. And remember, this T naught is not coming from constitutive relation. This is prescribed by the external agent. So this is prescribed. Prescribed traction. Externally prescribed traction. Okay, so this is just over S naught N dot eta ds naught. And then you have the other part also, no? The Dirichlet surface. So that surface, what is happening there? Because you have clamped your body over that surface. So what can you say about Pn over there? Anybody? Anyone? So on the Newman surface, Pn is T naught from the traction boundary condition. But what about the Dirichlet surface?
So it will be 0.
What will be 0?
Hello.
Yes. What is 0?
Because on the Euclidean surface, we are not defining any traction
But
from the outside.
but will there be action? There will be a reaction track because the body is
Yes, sir. Yes,
fixed.
because
So the support is going to apply some reaction on the body. So that means this part is not
yes.
0. So this is not 0 due to reaction from the surface or from the support. But then we choose our eta. Okay, so we choose our eta such that it vanishes on parts of surface where the body is let us say clamped, or you have prescribed the displacement of the body. If you have prescribed the displacement of the body, then you cannot perturb the body over there. See what is, so that's where now we are talking about some physics. What is the meaning of eta? So when we say it's a virtual displacement, it's like we are trying to perturb the body. I'll also say why it is virtual, but let us first see it's a displacement. So suppose body is in equilibrium, and then you are trying to perturb the body from the equilibrium. But when you perturb it, the parts of the body where it is clamped will not be perturbed, right? So therefore eta has to vanish there, because eta is the perturbation or the displacement of the body from equilibrium. So on those parts where the body is clamped, because you cannot perturb it, you cannot move the body, so eta must be 0. I hope it is clear to you. So this is also called admissibility criteria, this thing over here. So this decides the admissibility of virtual displacement or test function. Now, because of this admissibility, this eta is therefore 0 here. And therefore, this whole thing then becomes 0. Yes, go ahead.
Sir, can you please explain perturbation about equilibrium? Like, what do we mean physically by it?
Physically, it just means you are disturbing the body. So the body, you're applying some force, body gets deformed. So let me write down that picture. So here is that picture. This is the body which is clamped somewhere, and then you apply a force. Okay, so because of this force, the body may deform like this, right? But this part will be as it is, and this force may come down here. So this is the equilibrium configuration, whereas the green one is the reference configuration. Okay, and the pink one is equilibrium or deformed configuration. And we are thinking of further perturbing the body from this equilibrium configuration. Okay, so that will be the black one. So this perturbation could be arbitrary, it could be like this also, but it has to be smooth enough. So this is the perturbed configuration. Okay, so if a small f, if Fe is for equilibrium f, then f, let us say eta, which is equal to equilibrium plus eta. So this is the perturbed f. And now you can see when you are perturbing the body, because this part is clamped here, the green part, the green dashed line, you cannot perturb it. So therefore eta must be 0 over there, no?
So why we perturb?
Why you are perturbing? Okay. We are just saying what is happening to the equation when we perturb it. So when you perturb it, we are just trying to see what is happening to this equation. So think of perturbing this body arbitrarily and then see what happens to the equation. So you see this equation, that's a very good question. Why are you perturbing? So we have this equation right here, and I just want to see what happens to it when you multiply this with the perturbation and further integrate it over the entire volume. Okay.
So what is the motivation behind that?
What is the motivation behind that? As I told you, we are going to derive what is called principle of virtual work or the weak form of balance equation. And why we derive it? Because this is what is used in finite element method for solving.
Means how multiplying it by a virtual displacement and integrating it will lead to principle of virtual work physically.
So let us come to that, no? Let us come to the final equation and then you will see.
Okay, sir.
Yes. So as you can see, with such a admissible virtual displacement, this term is dropping, isn't it? This drops out. Not because Pn is 0, it is because eta is 0 there. So due to admissibility criteria, this drops out. So now let me write down the whole thing. So remember, this was just this part of the equation. And you have other parts also. So when you write down the whole thing together, you will get, let me use black color. So what you get is integration over the Newman surface of big T naught dot with eta ds naught. Okay, and you remember there is a body force term also, so that is an integration over the entire volume rho naught b dot with eta dv naught. Okay, and you see then you have this term over here, it's with a negative sign. Okay, so when you write down over here, substitute here, it comes with a negative sign, but you bring it on the other side. You see this whole thing is equal to 0, isn't it? Because the thing inside the bracket is 0 due to equilibrium. So when you multiply with eta, it will still be 0. And when you integrate over the entire volume, it is still 0. Okay? So when you bring it on the other side of equality, you get the following. Okay, now let us try to analyze what are each of the terms here. Can you see what is the physical meaning of, by the way, before doing that, this is what is called principle of virtual work. So this is called PVW. So there are two things here, virtual and work. So you might be wondering why I call it virtual work. So can you now, Pulkit, can you think of why are we calling it first of all work?
So because it is something like force multiplied by displacement. So
Which one?
like T naught ds, that will have
Yes.
unit of force.
Not ds naught. So that is the small force, right?
Yes, sir.
Acting on the surface. And as you perturb the body by eta, so that point where T naught is acting is getting perturbed by eta. So what will be the work done by T naught? That's simply T naught dot eta ds naught.
Yes, sir.
Similarly, the second term also you can see it is the work done by the body force, right? Because the force is rho naught b dv naught, the local force, and that the point where that force is acting is getting displaced by eta. So therefore, work done by that force is simply rho naught b dot eta dv naught, right? So
Yes, sir.
I'll just write this is the work done by body force and this is the work done by traction force. And what about the right hand side? What is this? So this is also called work done by internal stress. And let me make it more clear why is it so. At least for elastic case. So in elastic case, P is what? Del W by del F, right? Which is a function of big F, and it is then double contracted with gradient of eta. Now, think of small f of epsilon, which is equal to small f plus epsilon times eta. Think of this perturbation. So f is the f equilibrium. This is the equilibrium f. This is the equilibrium f, which is being perturbed by eta. And I have put an epsilon here. This is just to scalarize the differentiation. You can remember this is how we can scalarize the differentiation. Now, when you do this, what is happening to big F epsilon? Isn't this big F at equilibrium plus epsilon times grad eta? Right? So, due to this perturbation, what will be the energy stored? Energy stored will be simply W of F epsilon. Isn't it? And if epsilon is very small, what is this d by d epsilon of W? So you'll have to use chain rule, and I want to evaluate it at epsilon equal to 0. So that's del W over del F at F epsilon double contraction d by d epsilon of F epsilon. Okay, and the whole thing has to be evaluated at epsilon equal to 0. So this then becomes del W by del F at F double contraction. Now this thing you see from here, it is simply gradient of eta, isn't it? So this is, so basically this term is then from here, it's the change in stored energy due to perturbation. This is the change in stored energy due to perturbation, and which is called as the work done by internal stresses, because that is inducing change in stored energy. Am I clear to you? So you see on the right hand side you have work done by internal stress, whereas on the left hand side these are all external, by external body force, by external traction force. So this statement simply says that the work done by external agents is equal to change in stored energy of the body. Okay, so that's why this is a work, it's a work statement. You can also make it a power statement by saying that eta is virtual velocity. If you say eta is virtual velocity, that means it's a velocity instead of power. So instead of displacement, it is velocity. Then each of the terms, this one becomes power, right? Power of the traction, and this becomes power of body force. And the right hand side will be gradient of velocity, and then that becomes the rate of change of stored energy, power. Okay, therefore, we said it's either a virtual displacement or virtual velocity, and finally a test function. Now the most pressing question, why virtual? Can anybody tell me why virtual? So first of all, it's a work statement because each of the terms are related to work. But why virtual work?
सर एक डाउट था, मतलब जैसे ये एक्सटर्नल फोर्स, एक्सटर्नल ट्रैक्शन और एक्सटर्नल बॉडी फोर्स दोनों का मिला जुला इफेक्ट, ये जो ईटा है वो है क्या डिस्प्लेसमेंट उन दोनों के कारण?
नहीं, ईटा जो है ना इम्पोज किया जा रहा है, ये किसी का इफेक्ट नहीं है।
तो सर उनके
imposed by an external agent which can be arbitrary. ये किसी फोर्स के कारण नहीं, फोर्स जो लगा रहे थे ट्रैक्शन टी नॉट या बॉडी फोर्स, उसके कारण तो बॉडी इक्विलिब्रियम में आ गया, तो उसके कारण बॉडी इक्विलिब्रियम में आ गया, वहां पे सम स्मॉल एफ ई है, इक्विलिब्रियम कॉन्फ़िगरेशन। उस कॉन्फ़िगरेशन के ऊपर हम लोग एक्स्ट्रा ईटा लगा रहे हैं, so that eta is not an effect of anything. ये ईटा तो हम लोग लगा ही रहे हैं, ये किसी के इफेक्ट के कारण नहीं आ रहा, ये हम लोग इम्पोज कर रहे हैं।
ओके सर,
यस। और बस इस इम्पोजिशन का बस एक ही कंस्ट्रेन है कि इट हैज टू सेटिस्फाई दैट एडमिसिबिलिटी क्राइटेरिया, दैट it must vanish wherever the body has been clamped, तभी वो फिजिकल पर्टर्बेशन होगा, नहीं तो वो बस एक मैथमेटिकल पर्टर्बेशन हो जाएगा ना।
Eta will be a function of like small x.
Yes, not a small x. Eta is a function of big X. It's not a function of small x. Eta is a field. It is changing from point to point in the body. So eta is a function of big X. Eta does not depend on configuration of the body. Eta is arbitrary. As I told you, it is imposed by you. You can apply whatever you want. It just has to satisfy that admissibility criteria. So eta is arbitrary. It just has to satisfy admissibility. Any question?
सर
हाँ,
सर हम जो डिफॉर्मेशन इनिशियली दे रहे थे ट्रैक्शन जो बॉडी को अनडिफॉर्म कंडीशन से डिफॉर्म स्टेट में ला रहा था, लेकिन अगर हम ये ईटा इंपोज करेंगे तो वो कैसे करेंगे? क्योंकि हमने तो पहले पहला डिफॉर्मेशन जो दिया है वो हमने अट्रैक्शन के थ्रू दिया है, लेकिन ये ईटा देंगे वो कैसे होगा?
उसको पकड़ के बॉडी को पकड़ के घुमा, उसको हिला दो।
हाँ तो सर वो भी तो ट्रैक्शन हो गया ना, फिर
ट्रैक्शन हो गया, बट ये एक्स्ट्रा ट्रैक्शन, एक तीनों तो लग ही रहा है, भी लग ही रहा है, उसके ऊपर तुमने बॉडी को इम्प्यूज किया थ्रू या तो वो डायरेक्टली किसी फोर्स को लगा के कर रहे हो, या बॉडी को हाथ से पकड़ के उसको घुमा रहे हो, कैसे भी कर सकते हो।
तो सर हम लोग इसको डिस्प्लेसमेंट क्यों बोल रहे हैं? आई मीन
फाइनली ये डिस्प्लेस हो रहा है ना, इसलिए इसको डिस्प्लेसमेंट बोल रहे हैं। ईटा डिस्प्लेसमेंट ही तो हुआ ना, क्योंकि बॉडी डिस्प्लेस हो रहा है, वही डिस्प्लेसमेंट है ये ईटा। अब ये अब कैसे हो रहा है, दैट्स अ डिफरेंट क्वेश्चन, कि क्या हम लोग इसको सीधा पकड़ के इसको डिस्प्लेस कर रहे हैं, या फोर्स लगा के, एक्स्ट्रा फोर्स लगा के डिस्प्लेस कर रहे हैं। नॉट बाय टी नॉट एंड बी, टी नॉट और बी से तो वो इक्विलिब्रियम में आ गया, उसके ऊपर हम लोग डिस्प्लेस कर रहे हैं ये ईटा जो है। हमें एक्स्ट्रा फोर्स लगाना पड़ेगा, सीधा उसको पकड़ के तुम उसको कहीं पे लेके चले जाओ।
हाँ सर।
ओके, सो द फाइनल क्वेश्चन, व्हाई वर्चुअल? वर्चुअल का मतलब समझ ही रहे हो क्या होता है, इमेजिनरी, इजंट इट? इट इज नॉट रियल। if you go to dictionary, you will see that the meaning of virtual is it's not real. तो ये रियल डिस्प्लेसमेंट नहीं है, नॉट रियल। ऐसा हम लोग क्यों बोल रहे हैं कि ये रियल डिस्प्लेसमेंट नहीं है? एनी आइडिया? सबसे पहले तो उन्होंने कहा कि इसको फिजिकल डिस्प्लेसमेंट बनाने के लिए हम लोगों ने एडमिसिबिलिटी क्राइटेरिया लगाया, कि जहां पर बॉडी क्लैम्प्ड है वहां पर इसको वैनिश कराओ, ताकि सही में वो परटर्बेशन बन पाए। बट फिर भी हम लोग इसको वर्चुअल डिस्प्लेसमेंट बोल रहे हैं। कैन यू थिंक ऑफ व्हाई इट इज कॉल्ड वर्चुअल डिस्प्लेसमेंट? रियल नहीं है, अभी भी हम लोग क्यों इसको बोल रहे हैं कि रियल नहीं है? क्या हो गया?
सर डिस्प्लेसमेंट हो भी सकता है और नहीं भी हो सकता है।
नहीं, डिस्प्लेसमेंट तो होगा ही, क्योंकि हम लोगों ने लगाया है, तो डिस्प्लेसमेंट तो होगा ही।
ये ईटा डिस्टरबेंस है ना सर, बेसिकली इक्विलिब्रियम से है।
हाँ, इक्विलिब्रियम से है, यस।
सो जब हम वर्चुअल कंडीशन लेते हैं तो उसमें इसीलिए लेते हैं कि दैट मे बी इन एक्चुअल और मे नॉट बी आल्सो। तो वो जो ईटा है दैट मतलब ये हो भी सकता है सिस्टम में, और ये भी पॉसिबिलिटी है कि नहीं हो, तब भी ये वैलिड होगा, जीरो भी हो सकती है सारी कंडीशन।
इस कारण थोड़ी ना इसको वर्चुअल बोलेंगे।
सर हम यहाँ पे स्टैटिक इक्विलिब्रियम के बारे में बात कर रहे हैं सर। सो डिस्प्लेसमेंट एक्चुअली हो नहीं रहा है, बट हम एज्यूम कर रहे हैं।
नहीं, ऐसा क्यों बोल रहे हैं कि एक्चुअली हो नहीं रहा बट अज्यूम कर रहे हैं?
सर जहाँ तक मैंने पढ़ा था सर, हम ये
ऐसा सोचो कि
प्रिंसिपल ऑफ,
हाँ बोलो।
यहाँ पे हम इसलिए प्रिंसिपल ऑफ वर्चुअल वर्क अप्लाई करते ताकि हम ट्रैक्शन ड्यू टू फोर्सेस निकाल सकें, मतलब
अरे अप्लाई करते हैं ये क्वेश्चन नहीं है यहाँ पे। यहाँ पे क्वेश्चन है कि इसको वर्चुअल क्यों बोल रहे हैं।
सर डिस्प्लेसमेंट यहाँ पे वर्चुअल हुआ है सर, एक्चुअली
क्यों? ठीक है, बात गया तो इसको बोल रहे हो कि डिस्प्लेसमेंट वर्चुअल है
सर, क्योंकि पाथ कोई पार्टिकल डिस्प्लेस करेगा तो उसका पाथ अलग हो सकता है, और यहाँ पे हमने जो लिया है ये एक एज्यूम पाथ।
नहीं, ये दिस इज नॉट द आंसर
सर, क्योंकि इक्विलिब्रियम के बाद होगा नहीं में डिस्प्लेसमेंट।
हो ना, इक्विलिब्रियम होने के बाद तुम उसके ऊपर एक्स्ट्रा डिस्प्लेसमेंट तो लगा ही सकते हो ना।
Maybe I'm not sure.
Sir, work done by internal stress 0 होगा क्या?
वर्क डन बाय
इंटरनल स्ट्रेस
नहीं, जीरो क्यों होगा? उसके कारण जब अगर स्टोर्ड एनर्जी चेंज हो रहा है तो फिर जीरो क्यों होगा?
सर ये आर्बिट्ररी इसलिए
आर्बिट्रेरी
है ये डिस्प्ले,
तो क्या
लाइक
होगा?
ये फिक्स, मतलब ये फिजिकल मीनिंग नहीं है इसका। लाइक अगर कोई फिजिकल फोर्सेस लगते हैं इसके ऊपर तो एक पर्टिकुलर फाइनल कॉन्फ़िगरेशन मिलता है।
सर
नहीं, इसमें ही मान लो एक पार्टिकुलर ईटा ले लो, तो फिर क्या उसको बोलेंगे रियल डिस्प्लेसमेंट?
सर ये इसके रिलेशन सर डेरिवेशन से तो नहीं है, प्रिंसिपल ऑफ वर्चुअल वर्क से, जहां हम वर्क डन बाय रियल फोर्सेस को इक्वेट करते हैं वर्क डन बाय द वर्चुअल फोर्सेस।
Anyway, let me tell you the answer. तो सबसे पहला बात कि ये जो वर्क डन है इसको हम लोगों ने टी नॉट डॉट ईटा लिख दिया, राइट? टी नॉट डॉट ईटा कर दिया ना, बट एक्चुअल में वर्क डन क्या होता है? वर्क डन बाय अ फोर्स क्या होता है? लेट अस से बिग एफ। सो अगर ये मान लो इस पाथ पे किसी पार्टिकल पे लग रहा है ये फोर्स बिग एफ, तो ये पार्टिकल ट्रैवल कर रहा है पॉइंट ए से पॉइंट बी पे, सो वर्क डन जो होता है वो होता है एफ डॉट डी आर, राइट, इन इंटीग्रेशन ओवर दिस पाथ फ्रॉम ए टू बी, इजंट इट? और इसमें वो एफ जो है बाहर निकल सकता है अगर एफ कांस्टेंट हो तो, और फिर ये बन जाता है आर बी माइनस आर ए। सो दिस इज ओनली इफ f is constant. I'll say here if f is constant. अगर कांस्टेंट ना हो तो वो इंटीग्रेशन होता है, isn't it? अगर कांस्टेंट ना हो then we have to have this integration, क्योंकि during the displacement that big F is changing. Are you all okay with this?
Yes sir.
Here also you see we are saying that this is T naught dot eta. तो eta तो एक तुम्हारा perturbation हो गया, displacement. Now over that displacement अगर T naught change कर रहा हो, जो एक्चुअल T naught लग रहा है अगर वो चेंज हो कर रहा हो, जब हम लोग वो ईटा लगा रहे हैं और T naught मान लो अगर चेंज कर रहा है, तब तो हम लोग ये नहीं लिख सकते जो यहाँ लिखा है वर्क डन, तब तो एक एक्स्ट्रा एक और इंटीग्रेशन आएगा ना, यहाँ पर एक और इंटीग्रेशन आएगा ना, जो कि ओवर दी एक्चुअल पाथ ऑफ दी डिस्प्लेसमेंट लग रहा होगा, isn't it? Are you getting it?
Yes sir.
So likewise इवन जो बॉडी फोर्स में जो बी है, सपोज करो जब बॉडी को परटर्ब कर रहे हैं तो अज्यूम करो कि वो बी भी चेंज हो रहा हो ड्यूरिंग दैट परटर्बेशन, तो फिर तो हम लोग इसको ये नहीं लिखते हैं बी डॉट ईटा, So therefore, these are not the actual work done, these are virtual work done. क्योंकि हम लोग assume करते हैं कि the state of the body has been frozen, इसको फ्रीज कर दिया गया है और फिर इसको डिस्प्लेस कर रहे हैं। यानी फ्रीज करने का मतलब है कि जो टी नॉट है वही टी नॉट रह गया, जो बी है वही बी रह गया, और जो बॉडी के अंदर जो स्ट्रेस है पी, वही पी रह गया, और फिर उसको डिस्प्लेस कर रहे हैं। फिर तब जो वर्क होगा तब तो ये वही होगा, टी नॉट डॉट ईटा आ जाए, क्योंकि फ्रीज कर दिया गया है। ओके, तो राइट हैंड साइड में भी वो प्रॉब्लम है कि P अगर चेंज कर रहा हो तो एक एक्स्ट्रा इंटीग्रेशन आ जाएगा। तो ये तीनों का तीनों वर्चुअल है, तो देयरफॉर दीज आर ऑल वर्चुअल। दिस इज वर्चुअल, this is virtual, and this is also virtual. That's because we assume that the body has been frozen. यानी कि जो भी बॉडी के अंदर में स्ट्रेस लग रहा है उस स्ट्रेस को फ्रीज कर दिए, तो P जो है चेंज नहीं हो रहा है, B भी चेंज नहीं हो रहा है, T नॉट भी चेंज नहीं हो रहा है। फिर अगर डिस्प्लेस करेंगे तो यही वर्क डन होगा। ओके, अब तो तुम लोग कंफ्यूज नहीं हो गए ना क्या मीनिंग होता है प्रिंसिपल ऑफ वर्चुअल वर्क का?
सर
हाँ,
so eta is a small displacement or it can be anything?
it can be arbitrary, it can be large also. Okay, so I'll write that here. Eta need not be small. It just has to satisfy the that admissibility criteria. Okay, any more question? I think I should stop here because it is already 4. Okay, Vinayak also I think has to go. There are 4 of you who have to go for that meeting. Do you have any question? I'll stay here for some more time.
So, can you explain why exactly eta is a function of capital X?
कैपिटल X, क्योंकि
हाँ जी,
ये जो हम लोग जो परटर्ब कर रहे हैं वो रिजिड परटर्बेशन बॉडी के एक तो जहाँ पर ईटा जीरो होना है तो बाकी नॉन जीरो है, certainly it is not the same everywhere, therefore it's a function of capital.
but sir हम deformed body पे perturb कर रहे हैं ना?
हाँ, डिफॉर्म पे कर रहे हैं, बट ये लग्रांजियन हो गया, ये लग्रांजियन डिस्क्रिप्शन है, तो उसमें हर फंक्शन को तुम कैपिटल एक्स से बना सकते हो।
ओके ओके,
यस। Any more question?
सर
हाँ,
जब हमने जो बाउंड्री का जो पहला फर्स्ट इंटीग्रेशन था कि टी नॉट ईटा डीएस नॉट, उसको दो न्यूमैन और डिरिचलेट बाउंड्री में सेपरेट किया था।
हाँ,
तो अगर उस केस में मिक्स बाउंड्री कंडीशन रहता तो शुरू में ही,
हाँ, तो फिर तो उसमें जो है डोमेन में वो उसको तुम करके देखना, वो भी हो जाएगा। उसमें ऑफ कोर्स वो S0n और S0d नहीं बनता है, बट हर एक के लिए 3-3 कंपोनेंट होता है ना, तो उसमें से एक कंपोनेंट डिरिचलेट टाइप का होगा, एक कंपोनेंट न्यूमैन टाइप का होगा, तो उस तरह से बनेगा ये। तो उस तरह से परटर्बेशन भी जो होगा ईटा, उसका एक कंपोनेंट जीरो होगा बट बाकी दो कंपोनेंट आर्बिट्ररी होगा। जैसे यहाँ पे क्या है कि हम लोग बोल रहे हैं कि किसी पॉइंट पे तीनों कंपोनेंट ईटा का जीरो हो गया, बट अगर मिक्स टाइप का है तो ईटा का कोई एक कंपोनेंट स्पेसिफाइड कंपोनेंट जीरो होगा और बाकी दो जीरो नहीं होगा, उस तरह से लिखेंगे।
ओके
Okay, so I think I should go now because others are also missing out then.
Yes.
Thank you.
Okay, so see you then in the next class.
Yes. Thank you.
Thank you, sir.